Welcome back to my YouTube channel Tech Tips. Today we will see number system, but before that let us try to see why should we read this, why should we know this. First of all, the architecture and organization of a computer system depends partially on the type of number system that is being used in the computer. Okay, though there are so many other important parameters and issues to decide the architecture and organization of a computer, but number system plays a very little but vital role for a computing system, for its organization and architecture. Secondly, from our childhood level, we know the number system which is containing 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now onwards 10, 11, so and so. Okay. But whenever you are pressing a number, let's say 5 or let's say 75 from the keyboard, eventually computer means the CPU doesn't know the notation of 5. Okay, so it's converted into equivalent binary. Then that binary is understandable by the CPU, means the processor of a computer system. So whatever, not only the numbers, in the keyboard you will see there are various kinds of keys, numbers, alphabets, special characters, special symbols. So whatever you are pressing from the keyboard, each and every one is being converted ultimately into combinations of zeros and ones, which is easily understandable by the computer system. Okay, so as computer is playing with these numbers, okay, so we should know. In one more aspect, if you consider a variable in a programming language, let's say C programming, and you are trying to store a value within or against the variable, that variable is going to be stored into the main memory against a particular memory address. Okay, that memory address can be expressed as a hexadecimal number, obviously unsigned integer hexadecimal number. So far we have discussed, you can see, decimal number we have used from our childhood level. We can also use this number into computing. Eventually all the decimal numbers that we are entering, all the alphabet special symbols that we are entering from the keyboard is going to be converted into binary number. Thirdly, very common example, main memory address can be expressed as unsigned integer hexadecimal number. So far we have mentioned 3 names. One more name is there, that is your octal number. Okay. In some programming languages, we will see 0b, 0x, some prefix are added to express, to mean that this number belongs to binary, belongs to octal, belongs to hexadecimal number system. Okay. Now let us first see the general representation of a number in any number system. This is the decimal point against which you can write down D0, D1, D2, D3, up to Dm. Then D minus 1, D minus 2, D minus 3, D minus n. This part is known as the integral part of the number. This part is known as the fractional part of the number, and obviously it's known as the decimal point. So any number can be generally represented in this form. If we are writing an integer number, then this decimal point and the fractional part would be absent. If we are writing a fractional number, then this integral part will be absent. And if we are writing a mixture of integral and fractional number, let's say 5 or 58, it's a pure integer, no decimal point, no fractional part. And whenever you are writing 0.75, you can see no integral part is there. And if you are writing 78.95. Here you can see integral part as well as the fractional part, and the decimal point is there. Okay. Though we can consider, we can represent it using a decimal point and at least one zero. As we know, the zero after decimal point doesn't have any meaning. Okay. Similarly, before the decimal point, in this case, you can put a zero. Okay, so this is the very general representation, and D stands for digit, and this digit would be known as LSB or LSD, least significant bit or least significant digit. Similarly, this one can be treated as MSB or MSD, least significant bit or least significant digit. For a number, let's say 375, here you can see this is the LSB or LSD and this is the MSD. Okay, very fine. Now we will see the types of number systems. Types. So we can have, first of all, binary number system, which belongs to 0 and 1. These two notations, these two symbols. Next is octal number system, which is containing 0, 1, 2, 3, 4, 5, 6 and 7. Next is decimal, with which we are habituated from our childhood level. Decimal number system is containing 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. And the last one is hexadecimal number system. Hexadecimal number system, which is containing these notations 0 to 9 and A to F. 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E and F, where A can be thought of equivalent to 10, B can be equivalent to 11, C 12, D 13, 14 and F is 15. But we can't directly write here because this is the set of basic symbols of this number system, which should contain one notation, one symbol. If you are writing 10, 11, 12, 13 in this way, then you can see two notations, 1 and 0, 1 and 1, 1 and 2 are there. But we can't write this. But we can think of its equivalent value as 10, 11, 12, 13 up to 15. Okay. Now let us see the name, caption of each and every number system. Here you can see by. This by means die, means 2, means 2. Okay, so in total 2 symbols should be there in the basic set of notation. Okay, so that's why total 2 starting from 0. So we can move up to at most 1, 0 and 1. In total 2 symbols are there. And you can see each and every number system is starting with 0. Okay. Similarly, octal. Octal, from you know the series mono, di, tri, tetra, penta, in this way, octa, nona, deca. So from this octa you can see 8, which means 8, means in total 8 symbols would be there starting from 0. So we can move up to at most 7. Okay, so 0 to 7. Next is decimal, deca. Okay, deca means 10, means 10, means in total 10 different symbolic notations should be there in this number system. And eventually with this number system we are very casual, we are habituated with this number system from our childhood level. Okay. Now next is your hexadecimal. Octa, deca, hexa. Hexa means 16. Hepta, octa. Okay, so hexa, this means 16. So in total 16 different and unique notations would be there. You can see 0 to 9 means in total 10, then 11, 12, 13, 14, 15, 16. Okay, so if you count normally 0 to 9, then 10, 11 up to 15. Okay, so this is a very basic idea of 4 existing number systems, and it's very interesting. Okay, we can easily play with this number. Okay, some of us can also play with this binary, because in our school level, okay, syllabus, this binary number system has been included very nicely. May or may not be, we are habituated with octal or hexadecimal number, but if you are a student of computer science, or if you are thinking to read something, to do something with computer, to do some programming with computer, means computer language, then you should must know these number systems in details. Let us consider this number 8537. This number can be, and we have considered it as a decimal number system, but it can also be a hexadecimal number. Okay, but it cannot be an octal number system, because this notation 8 is there, and you know in octal number system the notation 8 is not there up to 7, 0 to 7. So from our childhood level we know one thing, that its units position means 1. Now this 1 unity, from where it's coming, from where it's being generated. So 10 to the power 0. Okay, 10 is the base value or radix value of this number. Now second position is hundreds position, and from where it's coming, 10 to the power, second position is tens position, 10 to the power 1. Now third position is 10 to the hundreds position, and from where it's coming, 10 to the power 2 means 100. Next is thousands position, and it's coming from 10 to the power 3, and so on. You can 10 to the power n or m. And as you know, these are the position values. As we have seen, if this is the decimal point, D0, D1, D2, Dm, D minus 1, D minus 2, D minus 3, D minus n. And this number doesn't have any fractional part, so that's why in our example this portion is off. Okay, only the integral part is there. So this D0, 1, 2, 3, these are the position value, position number. So base to the power position is giving you this unit, tens, 100, 1000, these positions. Okay, similarly in case of binary number system, let us consider 1101. It's also position value 0, 1, 2 and 3. Now as it is binary number system, so again its units position. Now this unity is coming from 2 to the power 0, not 10 to the power 0. Okay, because it's a binary number, so we will have to follow the base value of binary number system. Next is 2's position. From where? Means 2 to the power 1 equal to 2 means 2's position. Next is 2 to the power 2 means 4's position. Next is 2 to the power 3 means 8's position, in this way. So power of 2. Okay. Similarly in case of octal number system, r equal to 8, if you consider this 3, 7, 5. So again 0, 1, 2, its units position. Unity is coming from 8 to the power 0. Next is 8 to the power 1 means 8's position. Next is 8 to the power 2 means 64 position. in this way, so as a power of 8. And in case of hexadecimal, when r equal to 16, let's consider 3a 9c. Okay, in hexadecimal a b c d up to f is there. Again position value 0 1 2 3. So its units position means coming from 16 to the power 0. Next is 16th position, 16 to the power 1. Okay, next is 16 to the power 2, so 256 position in this way. Next is 16 to the power 3, 16 to the power 4, so on. Okay, so very common rhythm we can easily find out amongst all the number systems. So we are habituated with this from our childhood level with decimal number system. The same thought can be applied on binary, on octal, on hexadecimal. Only the base values would be changed. 2s, 4s, 6, 8s, in octal 1s, 8s, 64s, 1s, 16s, 256 in this way. Okay. So this concept would be useful in our later conversions of amongst number system. We will see later on. Now we will see one interesting tabular representation of these 4 number systems. Let us first draw the table. As you can see, r equal to 2. This r means the radix or base of the number system. R equal to 2 is binary. Then r equal to 8. Then r equal to 10. Then r equal to 16. Okay, so this is your binary. This is octal. This is decimal, and this is hexadecimal. Okay. Now let's complete it. Okay, 16. Now let us consider using this basic notation of binary number system, means 0 and 1, we can have these 4 combinations 0 0 0 1 1 0 1 1 of 2 bits. Okay. Now if we consider this one as a basic block, okay, now we will use this block 4 times. How many times? 4 times. So let us write it. 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1. So this is 1, this is 2, this is 3, 0 0 0 1 1 0 1 1. So we have written 4 times. Okay, the same thing we have repeated. Now let's find out a magical rhythm. The rhythm is, this is in the first column, you can see 1 0 1 1 1 0 1 0 1 0 1, means alternate 0 and 1 is there. Now as the base value of binary number system is 2 and the position is 0, as we have seen d0 d1 d2 in this way for integral part. So this is 0th position. So 2 to the power 0 means 1. So that's why 1 bit alternating 1 0 1 1 in this way. Next position is 2 to the power 1 means 2, means 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones in this way. So we are now getting a rhythm that in this column alternate 0 1 0 1 0 1. In the second column 2 zeros, pair of zeros, pair of ones, pair of zeros, pair of 1 in this way. Now next column would be 2 to the power 2 means 4, means 4 zeros, 4 ones, 4 zeros, 4 ones. Next column 2 to the power 3 means 8, So 8 consecutive zeros, then 8 consecutive ones. We can write many more. 2 to the power 4 means 16. So 16 zeros, 16 ones, 16 zeros in this way. Then 2 to the power 5 equal to 32. So 32 zeros, 32 ones. So in this way, day after day, we can write, we can enhance, we can enlarge this list, and similarly in the downwards. Okay, endlessly we can note down. But in our present discussion, we need up to this much. So that's why we are not extending it. Now we are habituated with this decimal number system from our childhood level. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so up to this much, these distinct notations are there. Now after 9, we generally write 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and so on. Now let's complete the octal. 0, 1, 2, 3, 4, 5, 6, 7, not more than that. Okay, because in the octal number system we are having only up to 7. So in total 8 distinct symbols are there starting from 0. So that's why we can move up to 7. Now after that 10 will come. Just like after 9 10 comes, similarly after 7 10 comes. This is the rhythm similarities. Now 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. Now let's complete the hexadecimal part. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E and F. Now after F, 10 will come. Because just like you can see 0 to 9, so distinct digit within the set is over. Now we will have to combine, we will have to consider the combination of these bits from 0 to 9. So 1, 0, you can see 1 and 0, 1, 1, 1, 2 in this way. Similarly, F is the very end of the basic set of unique symbols of hexadecimal number system. So similarly after F, automatically 10 will come. You may notice this one. In binary number system, only 2 bits, 0 and 1 is there. So obviously after 0 and 1, 10 is there. So after 1, 10, after 7, 10, after 9, 10, after F, 10. Getting? So in this way, if we extend 15, 16, 19, then 20 comes. Okay. And if we put virtual zeros in the left hand side of the unique bits of decimal number system, you can see from 0 to 9 in the left hand side all are zeros. In the right hand side 0 to 9. Now 10 to 19 in the left hand side all are ones. Again 0 to 9. From 20 to 29 all left bits are 2s and right bits are 0 to 9. So this 0 to 9 is being repeated in the right hand side, and in the left hand side zeros, 1s, 2s, 3s. In this way we can move. Similarly after 29, 30 will come. Now after 19 you can see 20 comes in our well-known decimal number system. Because all are ones and in the right side bit is 9, so no more bit is there. That's why we are bound to move to 20. So similarly you can see all are zeros in the left hand side for the octal. So all zeros, then in the right hand side 0 to 7, fine. In the left hand side, starting from 10 to 17, all are ones. In the right hand side, 0 to 7. So 0 to 7 would be repeated again and again in the right hand side. Okay. So similarly, 1 is over. Now 2, 0 will come here. in this way up to 2 7, then 30 will come just like this one. After 29 30 comes. Okay, all are 2's, right hand side 0 to 9, then 30. All are 2's, right hand side 0 to 7, then 30. So in this way it would be up to 37, then 40 will come. In this way we can write so many numbers of octal number system. And we can write very easily for the hexadecimal number system. We are habituated from our childhood level. Now let us consider the hexadecimal number system. Let's consider a meaningless zero for all the numbers. So similarly, in case of decimal number system, the same rhythm, okay, that we have seen for octal also. All are zeros, then 0 to 9. Similarly, all are zeros in the right hand side, 0 to F. Then in case of decimal, all are ones from 10 to 19. Then in the right hand side 0 to 9. Similarly 10, after that 11 up to 1F. So in the left hand side all would be 1, then right hand side 0 to F. So here this 0 to F would be repeated again and again, and in the left hand side digit will be increasing, starting from zeros, then ones, then twos, then threes, in this way. After 1F 20 will come. Then in this way 2F means it's equivalent to 29 in our well-known decimal number system. After 2F 30 will come. So now hopefully you can understand the rhythm, okay, with the help of our well-known decimal number system, how it's moving, how it's proceeding from one number to next number, and to next and so on. The same rhythm we can apply for octal number system, and we can move forward so and so endlessly. The same thing we can apply on our hexadecimal number system endlessly. The same rhythm. Okay. So this table is very nice and can be formed within a minute, rather within half of a minute. Okay. So no need to memorize all those things. Just try to generate this table in your rough page, in your exam hall. Okay. So maximum 30 seconds would be required for this, and that's why it's very helpful, because no need to memorize it. Okay. So no headache is there. Just repeat this basic block 0 0 0 1 1 0 1 1 4 times, and try to analyze column wise. In the rightmost column you can see 1 0 1 1, so alternate 0 and 1, because 2 to the power 0 equal to 1. Now next column, second rightmost column, 2 to the power 1 means position value 1 equal to 2, means a pair of zeros, pair of ones, pair of zeros, pair of ones, in this way. Next 2 to the power 2 equal to 4 means 4 zeros, 4 ones, 4 zeros, 4 ones, 4 zeros, in this way endlessly you can write. 2 to the power 3 equal to 8, so 8 zeros, 8 ones, 8 zeros, 8 ones, in this way. 2 to the power 4 16, okay. 2 to the power 20, 2 to the power 5 20, 32, in this way you can move. Once you have completed this binary column, then try to fill the decimal column. Write down 0 to 9 first. Here for octal write down 0 to 7 first. Here in the hexadecimal number system, try to write down 0 to F first, then come back to decimal number system. Okay. After 9 you can write 10. Similarly after 7 in case of octal you can write 10. Similarly after F in hexadecimal you can write 10. Okay. Now if you analyze, all are zeros 0 to 7, all are zeros 0 to 9, all are zeros 0 to F, same rhythm. Now all are ones from 10 to 17 in case of octal, 0 to 7, in this way. Hopefully you have understood very nicely, and you can easily generate this table within 30 seconds. Okay. Lastly, I want to put the common request to all of you. Please subscribe my channel and press the bell icon for upcoming next videos, and if possible try to share among your friends and known person. Okay. your such activities will inspire me for further videos and everything. Okay, thank you very much.